Synthesis-based design and implementation of analog electronic filters from low frequency to a few gigahertz. In MATLAB, the synthesis of analog filters is possible but limited. To extend these capabilities, SAFIMAM was developed a Graphical User Interface (GUI), created in App Designer that implements classical methods alongside the Pascal approach. Based on user-defined ripple, attenuation, and transition ratio specifications, the software generates key parameters such as filter order, transfer function, frequency response, and frequency transformations. Furthermore, it synthesizes LC ladder networks in both pi and T configurations, along with their corresponding impedance transformations. The proposed GUI, shown in Figure 1, consists of 5 main menus. The first menu allows the user to input the design specifications, view the computed filter order, and proceed with the synthesis to generate the LC network that yields the desired frequency response. The second menu of the GUI is activated exclusively upon selection of a Pascal filter. Within this menu, the user inputs the resistive value, RS, and specifies whether the filter is to be optimized for the passband or the stopband to proceed with the design. The first and third menus are displayed in Figure 2. To validate the results of the SAFIMAM GUI, filter synthesis is presented for 2 technologies, including both simulation and experimental results. The first example is a Pascal active bandpass filter optimized for the stopband for EMG signals, with a frequency range of 50 Hz to 3 kHz, using a bandpass prefilter with 20 dB attenuation and 1 dB maximum ripple. With these specifications and a transition ratio of 2, SAFIMAM generates results in which Chebyshev Type 1, elliptic, and Pascal filters optimized for the stopband exhibit similar responses with a third-order filter structure. The results summarized in Table 1 and depicted in Figure 3. To demonstrate SAFIMAM, a Pascal active bandpass filter, optimized for stopband performance and synthesized from a pi-type LC network, was selected. The passive network was actively simulated by replacing the inductors with components based on general impedance converters. The active architecture was implemented using FPAAs on the Anadigm QuadApex board and tested with the boat analyzer of the Analog Discovery 2. Figure 4 and Table 2 present the circuit schematic, experimental setup, frequency response, and the corresponding simulation and experimental results. The second design corresponds to a Chebyshev Type 1 bandpass filter for 5G technology applications, centered in the spectrum between 3.4 GHz and 3.79 GHz for microstrip patch antennas. The design specifications are maximum passband ripple of 1 dB, minimum stopband attenuation of 25 dB, and a transition ratio of 2.5. After entering this information into SAFIMAM along with the bandwidth and center frequency, the resulting T-type LC ladder network is obtained, as shown in Figure 5, followed by the impedance transformation. Table 3 compares the simulation and experimental results of the filter in a waveguide, showing agreement with the design specifications. The validation of SAFIMAM through the synthesis of both active and passive filters yielded promising results. When compared to the literature, the synthesized filters proved to be viable and reliable. Table 4 presents the key characteristics of the EMG and 5G filters. For the EMG application, the Pascal filter demonstrated competitive performance in terms of order, bandwidth, and attenuation, while the Chebyshev Type 1 filters for 5G exhibited results comparable to other studies. The experimental results aligned with the design specifications, confirming the software's effectiveness. Unlike other CAD tools limited to classical methods, SAFIMAM incorporates the Pascal approximation, thereby expanding the range of filter options tailored to specific design requirements.